All right, here we go. There's honestly nothing new here. All we're going to do is kind of put everything all together here, all right? And so what we're going to do is we're going to learn about free body diagrams, which I referenced, a few videos ago. It's essentially those little drawings, all right? The big difference is up until now, we've really just focused on the left and right forces, and we've kind of ignored gravity and normal force. Today, we're going to dig in, and we're going to draw every force that acts on the object, all right? So your objectives here, be able to make a free body diagram. You ought to be able to explain what a normal force is, and also tension is also in this video, okay? I know I mentioned it in some previous videos, but this is the first time we're actually gonna dig in, all right? So we're just gonna dive in, all right? So here we go. So today we're gonna learn about free body diagrams, all right? Often abbreviated free body diagrams. All right, and so a free body diagram is just a drawing of an object with all of the forces on it labeled at one specific instant, or occasionally like in a brief time interval. But it's just about what's happening kind of right now, all right? The drawing will also, if possible, include the following information kind of written off down to the side. Net force, acceleration, and then any information that you know about your velocity, all right? Like I say, we've already made drawings like this, but so far all of the examples we've just focused on left and right forces, okay? And so in the real world, we have vertical forces because there's almost always gravity, right? But until the last video, we didn't know how to calculate the force of gravity. But now we do. So we're going to apply that, all right? So here's going to be your general, this is like your little recipe for making a free body diagram, okay? And I'm actually going to tweak a little bit of this, looking at this right now. I'm realizing there's one little detail that I want to add, okay? So I'm going to move me over here. Let me get a slightly skinnier pen. Okay, cool. So the first thing you can do in your free body diagram is you're going to draw your object. Okay, if it's on a surface, maybe draw on the surface, and then identify the mass and the weight. When you do your free body diagram, weight, i.e. force of gravity, is always going to be the first force you draw. Box, mass, force of gravity, okay? The second thing you want to do is label any forces that are given, right? Like if the problem says Roy pushes the box, or a rope pulls the box, or whatever, draw those forces in, all right? And then the third part, this is the tricky part, this is where things get icky. All right, you got to stop and think about what you know, all right? So the first thing you want to do is think about, do you know the acceleration, okay? Now, specifically, you got to be careful here, right? Because so now we've got we're going to have forces. I'm getting ahead of myself. All right, so step one, if you know the acceleration, cool. Well, then if you know the acceleration, then you can use Newton's second law to find the net force, all right? And then usually what you'll do after you've done that is then you'll use the definition of net force to find some missing force, right? And you'll see all of this as we go through the examples, all right? Now, a lot of times you won't know the acceleration, but you'll know all of the forces. And if that's the case, then you use this equation first to find your net force, and then plug that back in up here to find your acceleration, all right? So, this is kind of the deal for this unit, all right? You're really just going to be dealing with these two equations, okay? Now, one other quick comment. Your object can have motion in two directions, all right? And so because we're just doing linear motion, our motion will always be either horizontal or vertical, all right? So I'm going to introduce one other thing here. So sometimes we're just concerned about the forces horizontally, all right? And if that's the case, I'm going to write this, net force horizontally, or acceleration horizontally. And that's just describing the motion kind of, along the surface that it could be sitting on, right? And sometimes the problem will be about a thing moving up and down. And in that case, we're going to be interested in our net force up and down and our acceleration up and down, okay? So these little subscripts, the x's and y's, are just meant to indicate sort of what direction we're worried about, right? Are we worried about the motion horizontally along the x-axis, or are we worried about the motion vertically along the y-axis, okay? And so what that means is a lot of times you have to run through this process twice, once horizontally and once vertically. All right, so I'll try to kind of model that as we go through these examples here, which is really the easiest way to do this. So here we go. So example number one, a 6-kilogram cat named Gordon jumps out of a tree. Make a free body diagram of Gordon while he's falling. So here, there's only motion vertically. I'm not going to worry about X's and Y's. Let's just do this. So here's our cat. Boop, 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 boop. He's got a tail. Hello, he's very cute. He's got some whiskers. Here we go, 6 kilograms. All right, so step number 1, identify mass and force of gravity. I already got my mass. I'm going to find my force of gravity by just doing 6 times negative 9.8 to get negative 58.8 newtons. And that's it, right? There's no other forces on him. He's in free fall. Okay, remember, we always ignore air resistance unless the problem specifically references it, which will happen. I guess we did in the last one, right? That weight worksheet. Okay, so anyway, all right, cool. So that's it. That's the only force. So I know all my forces. So now I can find my net force. It's going to be negative 58.8 newtons down, if you want to be picky about it. And so I can find my acceleration. It's just net force over mass, but I already know it's going to be negative 9.8 meters per second squared. All right. So there we go. That's about as hard as, or about as easy as they get, right? Okay. So how about this? Roy holds a 14 kilogram box in his hands. All right, cool. So here we go. 14 kilograms. That means gravity is going to be pulling it down with a force of, oh, I'm sorry, I should have written these out. 137.2 newtons. All right, now notice it's not on a surface here. I wish I hadn't drawn this. So it's this, right? Okay. Now, he's just holding it in his hands. I wish I had written at rest. All right, so since it's at rest, what that means is our acceleration is 0, which means our net force also has to be 0, right? Because it's not moving. He's just doing this. He's just holding the box in his hands, right? All right, and since the net force is 0, that means there has to be an upwards force. Where does that upwards force come from? Oh, well, it's coming from Roy, right? Gravity's pulling the box down, right? And he's pushing up to prevent it from falling. All right, and so since our net force has to be 0, that means the force of Roy has to be negative 137. If you're somebody who's driven by equations, it's this. Net force is force of Roy plus force of gravity. My, boop, 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 boop. My net force is 0. Force of Roy, I don't know. Force of gravity is negative 137.2. Add force of Roy has to be 137.2 newtons. Now, do you need to write all that out for this one? No. But as the problems get more complicated, this process will make your life easier. Okay? All right, so there we go. That's our free body diagram. All right, so now this next one, it's almost the exact same thing, except this time, instead of the box sitting at rest in Roy's hand, now it's sitting at rest, whoop, on a table. All right, it was important that I moved the camera for that. All right, so here we go. So now here's our table, box, 14 kilograms. Force of gravity is negative 137.2 newtons. It's sitting at rest on the table. Oh, that means it's not moving. Oh, that means the net force is 0. Something has to be holding it up. What is it? The table. Oh, that's an inanimate surface. So I just call that normal force, right? And it's got to be 137.2 newtons. All right. So remember, we learned this a couple of videos ago, but remember, the support force provided by the table or any inanimate surface is called normal force. It is always perpendicular to the surface, okay? So that's my free body diagram on this one. Now, a word of caution. So there's my free body diagram. A word of caution. In this example, it happens that the normal force is equal to my gravity, right? They just cancel one another out. That is not always the case. All right, write this down. When you're doing vertical forces, normal force is always your last vertical force. Okay, and I'll show you why. I hope that the next example is the one that I think it is. It's not. Darn it. All right, I'm going to skip example 4 for a minute. I'm going to come back to it. And I'm going to go all the way down here to number 6. Okay, so I'm jumping ahead to example number 6, and I apologize. All right, so here we go. So we got a 12 kilogram dog sitting on the ground. 12 kilogram dog, force of gravity, 12 times 9.8 gives you negative 117.6 newtons. All right, so that's how you start every free body diagram. Second step, any given forces. Oh, Sally pushes him down with 50 newtons. force of Sally, negative 50 newtons, right? And then step 3 is think. So what's going to happen? You've got this, the dog is, here's my dog, in the form of a calculator sitting on the desk, and Sally pushes down. Well, that's not going to make the dog move, right? I'm just pushing down on it. And so what that means is, oh, my acceleration is still 0, which means my net force has to be 0. Which means, well, let's see. What's preventing the dog from moving down? Oh, that normal force from the table again. But how big does it need to be now? Now the normal force needs to be big enough to cancel both of these, right? Mathematically, its net force is force of gravity plus force of Sally plus normal force. The net force has to be 0 because the dog is not moving. Force of gravity is negative 117.6. Force of Sally is negative 50 plus something, right? And so that one normal force has to cancel the 2 downward forces. So it looks like you're going to get, what is that, 167.6 newtons. All right? So your normal force does not always have to exactly equal your gravity, okay? What the normal force is doing is it's essentially providing exactly enough force to prevent the object, in this case the dog, from moving through the surface, okay? Cool. All right, there's another normal force example here in a minute, so we will get there. All right. All right. So in number 4, we've got a piñata hanging from a rope tied to a tree. So here's my piñata, 5 kilograms. All right, gravity's pulling it down with a force of 5 times 9.8, so 49 newtons. But again, it's just hanging from a rope tied to a tree. So if it's just hanging there, then again, my acceleration 0. That means my net force is 0. What's holding it up? Oh, the rope. So remember, the rope, force of the rope we call tension. So force of tension is, well, it's got to be enough to make my net force 0. So it's got to be positive 49 newtons, right? So in a lot of situations, your tension works kind of like the normal force, right? It applies just as much force as it needs to prevent the object from, moving up or down, kind of. It's a little sloppy, but all right. So there we go. So that's how you deal with tension. All right, now this one. So I did this one in the video a couple days ago. It says Sally pushes a 3-kilogram painting horizontally against a wall with a force of 50 newtons to prevent it from sliding down the wall. So this time, my surface is vertical. Here's my painting. It's 3 kilograms. So the first thing I'm going to do, let's change colors, is put in my force of gravity. I said let's change colors. So let's put in our force of gravity. So 3 times 9.8, you're going to get negative 29.4 newtons. It says Sally pushes it horizontally with 50 newtons. That's weird. Force of Sally, 50 newtons. All right. Let's see, and it's negative. So now I've got both forces up and down and left and right. So let's think about what we know. All right, well, first of all, I know it's not moving at all horizontally. So I know my acceleration horizontally is 0. Oh, that means my net force horizontally has to be 0, right? There isn't any net force left or right. So if Sally's pushing the box this way against, or the picture this way against the wall, well, the wall is going to prevent it from moving by pushing back with a normal force. Oh, here's another example where your normal force doesn't equal your gravity, and it's not even up and down, right? This time it's left and right, because remember, your normal force is always perpendicular to the surface, okay? All right, now, so that's that. Now it's not sliding down the wall. The word sliding is always a good clue because it's telling us to think about friction, right? So the idea is it's not accelerating vertically either, which means I can't have any net force vertically. So what's preventing it from sliding down the wall? Friction. So my force of my force of friction has to be positive 29.4 newtons to prevent it from sliding up or down. Okay, so this is a good one because it illustrates this idea of having sort of 2 net forces and 2 accelerations, right? This trick here is going to be really, really important moving forward, where you're going to have to think about horizontal net force, vertical net force. All right? All right. And we already did example number 6. Example number 7. Oh, so we're back to this dog. The dog sits on the ground, and now Sally, let's see, so in the last one, Sally was pushing the dog down. This time, the dog is on the ground, and Sally's going to lift him up. So here's our dog, 12 kilograms. Force of gravity is negative 117.6 newtons. Force of Sally, 50 newtons up. Make a free body diagram. All right, so notice I again started with mass and force of gravity and any given forces. This time there's nothing horizontal, so I'm not going to worry about x's and y's. It's all about up and down. So the question is this. Sally lifts him up with a force of 50 newtons. Now, the fact that she lifts up, I guess maybe I should have chosen a different verb here. I should have said maybe attempts to lift him up. Probably would have been better, and I think the homework is worded that way. So, is 50 newtons enough to lift a 117 newton dog? Well, no. Right now my downward forces are winning, right? So if I stop here with my drawing, my dog is moving down. But the dog can't move down because he's already sitting on the ground, right? So I'm like, it's like, I'm going to lift my desk, right? Oh, I can't see. Oh, I'm trying to lift my desk, right? Oh no, that's not enough force to lift it, right? So, it's not going to move. Oh, that means my net force has to be 0, doesn't it? Why isn't it moving down? Oh, there's a normal force. The floor, the ground, is still in the way. So how big does the normal force have to be? So I'm going to go net force is force of gravity plus force of Sally plus normal force. Okay, so my net force is 0 because the table's not moving. Or sorry, the dog isn't moving. Force of gravity is negative 117.6. Force of Sally is positive 50 plus something, right? So it looks like this is going to have to be 67.6 newtons so that my 2 upward forces cancel my 1 downward force. All right? All right. I think we can skip this example. All that's happening is now Sally's exerting just enough force to cancel the gravity. So you're going to have gravity. I guess we're not skipping it, huh? So gravity's pulling down with 176 newtons. Sally's trying to lift it. Sally's force is 117.6 newtons. She's exerting just enough force to prevent it from falling, but not enough force to actually make it move, right? And so in this example, my net force is going to be 0. My acceleration is 0. And the table, I could literally take it out and the dog wouldn't, or the raccoon, I guess. Why did I change it to a raccoon? Would not be moving, right? He's just hanging out, okay? All I've done is take the weight off of the ground, and now Sally's supporting the weight. Kind of a dumb example. All right, now, here's the important thing, though. So in this example, Sally's force was 50 newtons, which is less than he weighs, right? So because her force was less than the dog's weight, he didn't move, right? That's why the acceleration was 0. Now here, Sally's exerting just enough force to support the weight, but not enough to produce a net force. So now in this last example, or next example, oh, I skipped example 9. So in this example, Sally's lifting up with a force that's more than the force of gravity. So here's the dog, ground, 12 kilograms, gravity, 12 times 9.8, force of Sally. So now, once again, if Sally's trying to lift the dog, is 150 newtons going to be enough? Well, yeah. 150 newtons is more than 176 or 117.6, right? So it looks like the dog's going to move, and he's actually not going to be on a surface anymore, right? Which means now my net force is the force of Sally plus the force of gravity, which is 150 newtons up minus 117.6 newtons down, which gives, what is that, 32.4 newtons, I think? So there's our net force, which means I can find my acceleration by doing net force over mass. So I'm going to take 32.4 newtons and divide it by 12 kilograms. I'm going to use this calculator, 32.4, oops, clear, 32.4 divided by 12 gives us 2.7 meters per second squared. So this time the dog is actually moving upwards because Sally's force was enough to lift him. All right. All right. All right, so now it says Roy uses a rope, so now we're back to tension because it's a rope force, to lift an 8-kilogram box of gummy worms, upward from rest with an acceleration of 4 meters per second squared. Make a free body diagram of the box 3 seconds after you began lifting it. So it's describing an instant in time now. All right, so here we go. 8 kilograms. So I'm going to start with my force of gravity. So remember, force of gravity, mass times 9.8, mass times 9.8. So 8 times 9.8 gives me 78.4 newtons down. I'm going to go ahead and make it negative. The problem tells me that the acceleration is 4 meters per second squared. It's going from rest. So after 3 seconds, let's see, my velocity is going to go up by 4, 3 times. So now my velocity is 12 meters a second. All right, so let's see. Oh, I know the acceleration, so I can find my net force. So I got an 8-kilogram thing accelerating at 4 meters per second squared. That gives me 32 newtons. 32 newtons. Please notice that is the net force. So what other force is on my drawing? It's got to accelerate upwards, so I need an upwards force. Oh, that's the force of the rope. Remember, force of rope we call tension. And so the question is, what does it need to be to make this my net force? So here I go. Net force is tension plus gravity. So I need 32 net newtons upwards as a result of tension minus stupid gravity pulling down. So add 78.4 to both sides, and your tension turns out to be, what is that, 110.4? Yes, 110.4 newtons. All right. Notice the upwards force is winning, producing an upwards acceleration. Okay. All right. Oh, I think we're almost done. Oh, man. More examples than I thought. All right. All right, so now we have a 160 kilogram pony. 160 kilograms. So gravity is going to pull down with a force of 1,568 newtons. Is that right? Sorry, I don't know. I didn't write these out first. 160 times 9.8. Yes, sir. Okay. So that's always your first thing you put in your force of gravity. That says kilograms. All right. Roy's pushing the pony to the left with 960 newtons. So here's my, I'm going to have normal force and norm. So I'm actually going to write norm's name here. It's going to be negative 960 newtons. Let's see. This problem is worded horribly. We got to assume that the pony begins at rest. So if norm's pushing to the left, then my velocity is going to be to the left. It looks like after 2 seconds, I can maybe find that velocity. It tells us friction is 320 newtons. So if the attempted motion is to the left, then the friction is going to be to the right. Remember, friction resists motion. Friction resists motion. It doesn't resist force. It resists motion. That's going to be really important. All right. Cool. All right, so now, again, I've got forces in 2 dimensions, don't I? So let's deal with vertical, first of all. There aren't any up or down forces sort of trying to lift the pony. So what that means is my acceleration vertically is 0, which means my net force vertically is 0, which means if gravity is pulling down, there's got to be something holding it up. And that something has to be the normal force. And in this case, it's just enough to cancel out gravity, right? Because that will make all of this 0, right? Cool. So now notice normal force is the last one of the up and down forces I put in. All right. So now we got to deal with the horizontal motion. So here we got 2 horizontal forces. We got norm and friction. So now my net force horizontally is the force of norm plus the force of friction. So we're going to get negative 960 newtons plus 320 newtons gives us negative 640 newtons horizontally. And so now I can find my acceleration horizontally by doing my net force horizontally divided by my mass. So that's negative 640 newtons divided by 160 kilograms. So it looks like I'm going to get negative 4 meters per second squared. is my horizontal acceleration. Now, on a lot of my answer keys, because I've written them a while ago, sometimes it'll just say acceleration is -4 meters a second squared, and it won't specify horizontally. I'm working on updating all of those answer keys. So let's try to get in the habit of distinguishing between horizontal and vertical, okay? All right, so I think that's it, yeah? All right. Okay, so here's another one where I've given you the acceleration, but we're missing a force. How do we know we're missing a force? You don't know that, but I do. So here we go. So Gus slides a 60 kilogram copy machine. So 60 kilograms. Let's go ahead and put in our force of gravity. It's going to be 588 newtons. He's going to slide it to the left. So here's our force of Gus. Oh, shoot, another G. Force of Gus with a force of 270 newtons. It accelerates to the left at 2 meters per second squared. Oh, shoot. 2 seconds. I guess I could have found my final velocity, right? Here, the acceleration was -4, so after 2 seconds, the velocity is going to be -8 meters per second. Okay. So here we go. So this guy is accelerating to the left at 2 meters a second squared. Here it doesn't give us a time interval, so this is what's happening. All right. So once again, let's see, my net force vertically is going to be 0, right? Because there's nothing pushing up or down in an attempt to lift it, kind of. So my net force vertically is going to be 0. So this needs to be canceled by a normal force of 588 newtons. All right, which means my acceleration, or I guess I should, other way around, right? Acceleration vertically is 0. This acceleration here is, in fact, horizontal, right? And so I can find my net force horizontally by doing mass times acceleration. All right, cool. So there's my net force horizontally. So now I can figure out what the force of friction is, right? Because my net force horizontally is the result of Gus and friction. So let's see, -120 newtons equals -270 newtons plus something. Math, 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 add 270 to both sides, and your force of friction turns out to be positive 150 newtons. All right, I think we're almost done. Yes, okay, yep, one last example. Okay, shoot, remind me, in class tomorrow when I see you, or whenever I see you next, please remind me, I want to show you an example that illustrates friction opposes motion. Somebody remind me in class that I have to show you an example about that, okay? Because that's the most commonly missed thing, all right? And I'm surprised I didn't put one here in the notes, but it will be a good opportunity for you to ask questions about the video. So let's do this last example. All right. So here's another example. So usually normal force sort of prevents an object from moving up or down, right? Watch this. So here we have a 40 kilogram box of donuts. Okay, so that means gravity is going to be pulling it down with 40 times 9.8 or 392 newtons. Now the elevator is moving up. Elevator is moving up. As it reaches the top floor, the elevator decelerates. So that means my acceleration vector is going to be down. So that's going to be -2 meters per second squared. All right. Well, this doesn't make sense because right now my only force is gravity. So it's got to be it would be falling down at 9.8, but it's only accelerating at 2 meters a second squared at negative, right? So what are the forces there? Well, the box is touching the floor of the elevator. So there's an upwards force here, a normal force because it's coming from an inanimate surface, all right? And this is how the elevator is pushing the box, right? A lot of times students put in both normal force and force of elevator. No, the normal force is the force of the elevator, right? So what's happening is, let's see, the elevator is moving up, but slowing down. So in order to stop the upward motion, right, remember right now the box is moving up. So to stop the upward motion, we need more force downwards. We need our net force to be downwards to stop the upward motion, right? So let's figure out what our net force is. It's going to be 40 kilograms times negative 2 meters a second squared. So our net force has to be negative 80 newtons. So right now my net force is negative 392 newtons. So my normal force is going to apply just enough force such that when I do normal force plus gravity, I get this net force, right? So let's see, net force is gravity plus normal force. So the net force is negative 80, gravity is negative 392. I don't know what my normal force is. Add 392, normal force turns out to be 312 newtons. So have you ever noticed when you get to the top floor on the elevator, you feel light for a second? When Frank and Sally were younger, they used to like jump when they got to the top floor, right? Like, ooh, I feel lighter, and you feel like you can jump super high. The reason you're feeling lighter is because the elevator is not pushing up on your feet with as much force anymore, because it's allowing gravity to win to slow your upward motion. All right? Okay, lot in this video. I hit just about every example. The only one I didn't hit was this, all right? You guys are gonna have questions. This is like the next 3 weeks of this class is these free body diagrams, all right? So please make sure that you come in with questions when I see you next time, all right? There's a lot going on here, okay? All right, that's what I got for you.